it's Matt from Audio Workshop and welcome to part 2 of radio wireless microphones. In part 1 we looked at what makes up a radio wireless system, we looked at the components and we gave a basic overview of how those worked. Now when watching the video back I realised I'd made a bit of a boo-boo. When we were talking about modulation, and in particular AM, I had stated that the dynamic range of AM was 90 dB. Well, in fact, that is completely and utterly wrong. AM's dynamic range is only 50 dB. So, now I've put the record straight, we can move on. And today I wanted to talk about basic radio principles. Radio refers to time-varying electromagnetic fields created by varying voltages and or currents in a particular source. Now this can happen naturally or artificially. Naturally would be in the atmosphere when we see lightning, for example, whereas artificially is electrical power or electronic circuits. Now when we see varying electromagnetic fields radiating out of a source over distance, this is what we call a radio wave. Radio waves have two fields. They have an electric field and they have a magnetic field, which are 90 degrees opposed. So if we were to dissect the wave, we would see something looking like this, where we have an electrical field and we have a magnetic field. Now depending on the angle that the electrical field is at, determines the polarization of the radio wave. Now this is taken into consideration a lot when we're talking about designing antennas by the manufacturers. Now, radio waves can be very similar to sound waves, and some of the terms we use to describe them are definitely the same. So we're often found talking about frequency, magnitude, and wavelength, and it's no different for radio waves. Frequency is a time-based measurement where we're looking at how long does it take for the variation to occur before it repeats. So frequency, like sound in this case, is measured in hertz, where 1 hertz equals 1 cycle per second. In sound, we're talking about the range of 20 hertz to 20,000 hertz, which relates to our human hearing. But with a radio wave, we can often be talking about kilohertz, megahertz, and even up to gigahertz and millions of gigahertz, where we start talking about light. Sound travels a whole lot slower than radio waves. Sound travels at 343 meters per second, whereas radio waves travel at 186,000 miles per second, which is the speed of light, so a whole lot different. When we talk about magnitude, when we're talking radio waves, we're talking about the strength of the variation. And when we're talking about wavelength, we're talking about the distance it takes for the wave to travel 1 cycle. Same with sound. Now one of the key things we need to understand with radio waves is how they propagate. With sound propagates through air. With radio waves, they prefer a vacuum. In anything other than a vacuum, it actually starts to affect the signal strength. One of the things that radio waves really react to is metal, and with metal they actually get reflected, and it's the only material that does reflect a radio wave. Now this is determined by the wavelength versus the size of the medium. So if we've got a radio wave that's equal to or smaller than the medium, it will reflect. If the radio wave's larger than the medium, in this case metal that we're talking about, it will actually go around it. But it's important to realise that metal does deteriorate the signal quality of radio waves because it's reflecting the energy or the wave. It also attenuates that wave, so it loses signal strength. Now radio waves travel through all other mediums just fine, but they do lose again signal strength. And human bodies is actually one that attenuates it quite a lot. So we need to take all of those into consideration when we're planning our RF, particularly in terms of install, but also live sound as well. And we want to make sure that we're getting enough RF signal to the receiver, which we'll talk about more in detail later down in the series. But it's important to know that over time over distance, a radio wave also deteriorates in signal quality. With sound, we talk about inverse square rule, where we double or half the distance, we lose 6 dB of level. Now, with a radio wave, this is no different, so the same principle applies. If we double or half the distance, we are starting to either gain or subtract by a factor of 4 in terms of its signal strength. So we just need to be aware that distance, we reduce signal strength. With reflections off metal, we reduce signal strength. And radio waves going through any other mediums, whether it's a wall, a window, a door, it's still reducing signal strength even though it goes through. And in RF wireless system, the loudest signal wins. So we're going to talk a bit about that as we continue through the series. I hope some of this has made sense to you. I know that as we get through the series, it's going to make more sense in terms of applying it once we're talking about getting the most out of your system in your environment. Hey, so thanks for tuning in, and we'll see you again tomorrow for more wireless microphone tips. Cheers. Bye-bye.